Hello and good evening. On behalf of the Astronomical Society of India, it is my pleasure to welcome all of you to the Professor M.K. Vainu Bappu Gold Medal Lecture online session. Also present with us today is Professor Dipankar Banerjee, recipient ASI.
Secretary,
I will begin with a few words about the award. The Astronomical Society of India, ASI, has instituted a fund in the memory of Professor M.K. Vainu Bappu. Professor Bappu was an Indian astronomer known for the discovery of the Wilson-Bappu effect, was the first president of the ASI, the president of the International Astronomical Union, and laid the foundation of modern astronomy and with telescope facilities in India. The award was instituted with the dual objectives of promoting the knowledge of astronomy and astrophysics, as well as honoring the contributions made by young scientists from any part of the world in the field of astronomy and astrophysics. This session is organized for the award lecture by Dr. Eve Lee, the recipient of the gold medal for the year 2022. I welcome Dr. Lee to the session. I first invite Professor Banerjee to say a few words.
Good evening. It's a pleasure for me to introduce Dr. Lee. Rather, I will just hand over this to my colleague, to Dr. Anupama. But just on behalf of the Astronomical Society of India, I would like to congratulate Dr. Lee. We would have loved to have Dr. Lee in person, but because of her busy schedule, she couldn't make it during our annual meeting. But we are hoping that in the near future, she'll be able to visit India, and we'll like to have her in one of our research institutes as a guest as well. So thank you again and congratulations. And I will request Dr. Anupama to take it forward from here.
Thank you, Dipankar and Sarita. Welcome to this session, Eve. It's a pleasure having you giving the Vainu Bappu Award lecture today. And congratulations on having received the award. Let me just give a very brief introduction to Dr. Eve Lee. She is an alumnus of the University of Toronto, where she did her BSc and MSc. She did a PhD in 2017 from the University of California, Berkeley, on the topic of the late-time formation and dynamical signatures of small planets. While at the University of Berkeley, as a PhD scholar, she received the prestigious Mary Elizabeth Old Prize for outstanding scholarly achievement. And subsequently, she was a postdoctoral fellow at Caltech, where she got the Sherman Fairchild postdoctoral scholar as a she was at Caltech. And then in the year 2019, she moved to McGill University as an assistant professor. At the McGill University, she has been the recipient of the William Dawson Scholarship. And in the year 2022, she was also awarded the Annie Jump Cannon Prize by the American Astronomical Society. And, as this lecture says, that she was the awardee of the 2022 Astronomical Society of India's Vainu Bappu Award. Now, a very brief introduction to her science. I will read out the actual citation of the VB Award, which will tell you about her science achievements. The citation reads as follows. The Professor M.K. Vainu Bappu Gold Medal Award of the Astronomical Society of India for the year 2022 is awarded to Dr. Eve Lee of McGill University, Canada. Dr. Lee is an expert in the field of exoplanet formation and has shown significant creativity in developing new models for explaining the unexpected diversity of the exoplanets, from the rocky planets to the gas giants, these planets that have been discovered so far. And this she has done using fundamental physics and astrophysics. Her work has defined paths forward for the exoplanet community, motivating new theoretical and observational initiatives. She is responsible for coining the term superpuffs for a rare class of exoplanets that are too voluminous for their small masses, and has provided for the first time a theory for their origin. Dr. Eve Lee is awarded a 2022 ASI Vainu Bappu Gold Medal in recognition of exceptional work in the study of exoplanet formation, large number of refereed publications, and an excellent record of citations. With this, I'll now invite Eve to present the Vainu Bappu Award lecture. Over to you, Eve.
Thank you so much, Dr. Anupama, for the very kind introduction, and also Dr. Sarita and Dr. Dipanka for inviting me and also arranging for this special lecture. So let me now share screen. Just want to make sure that it is sharing properly.
Yes, we can see it. It's fine.
Okay, great. Okay, great. Thank you so much. All right, it's a huge honor for me to be selected as a recipient for Professor M.K. Vainu Bappu Gold Medal. And again, huge thank you to the Astronomical Society of India for arranging for this special virtual lecture. So at McGill, I'm leading a theoretical astrophysics group studying the formation of planets and stars. And while our research approach is theoretical, almost all of our questions are motivated by some of the puzzles that have emerged in the observational data, like the trends and patterns that we see in the properties of the exoplanets. And in fact, from the observational perspective, we have access to two endpoints of planet formation. First, we have access to the initial condition of the planet formation from the observations of the protoplanetary disks. These are the spinning disks of gas and dust surrounding young stars. Here's a famous image, H. Tau from ALMA. We now know that a lot of the nearby disks have these beautiful substructures, these rings and gaps that could be a signature of the planets. And at the other end of the spectrum, we have access to the final product of planet formation given by the discoveries and characterizations of the exoplanets. But purely from the observational perspective, we don't have a direct access to what happens in between. And that's where the theories come in so that we can study what kind of paths do these planets follow to go from that initial condition to their final product. And there are different ways to go about this, but for this discussion, for this lecture, I will show you how we can go from this final product and use some first principle physics and astrophysics to try to go back in time to figure out their origin stories. So let's first zoom in to this final product, these exoplanets. These are confirmed exoplanets drawn from the NASA Exoplanet Archive with the measured masses on the y-axis and the orbital periods on the x-axis. They're color-coded with respect to the different detection methods. What was really striking when we found this thousands and thousands of exoplanets is that they are really diverse. We see for any given orbital period, we see at least about 4 orders of magnitude variation in their measured masses, especially at the short orbital periods where we have the most complete sample of the exoplanets. You might notice that this region of the parameter space is quite sparse. We don't see any planets. That's not necessarily because they don't exist. It's just that it's very difficult to detect these planets, small planets, at long orbital periods. And what is a bit unfortunate is that that's exactly where our solar system planets lie. We happen to live in a system with small planets at long orbital periods. So in other words, we don't yet have the technical capabilities to detect a true solar system analog. But we can still say that our solar system is unique in that we don't have any of this short period planets. And furthermore, we have no planet of the size between that of the Earth and Neptune. And that's quite surprising in sort of retrospect after we have found all these exoplanets, because turns out these are exactly the types of planets. These are exactly the types of planets that are the most common in the exoplanetary data, at least among those that we have detected thus far. And that is the most easily seen when we take a look at the measured sizes of the planets. It's much easier to detect the sizes rather than the masses of the planets. So here are the size of the planets on the y-axis. Instead, we see this huge clump over here. And with the more careful statistical analysis, we now know that about 30 to 50% of all sun-like stars have at least one of these small short period planets. So you'll note that I have labeled them as either super Earths or mini Neptunes. Until about a few years ago, we used these two terms interchangeably. But nowadays, we can't do that because turns out these are physically distinct. So super Earths are the scaled up version of the Earth. These are about 1 to 1.6 Earth radii, and these are rocky planets. The mini Neptunes are the scaled down version of the Neptune. So 1.6 to 4 Earth radii, and to explain their measured masses and sizes, they must have some significant hydrogen-helium atmosphere on top of their rocky core. So by comparison, these large planets at short orbital periods, these hot Jupiters, they are much rarer. Only about 1% of sun-like stars have these hot Jupiters. So why is it then that our galaxy prefers the formation of these small planets as compared to the large planets? And taking a step back, just more generally, how can we explain this huge diversity of the exoplanets and their overall population? What exactly shapes that? So what are the key parameters that control whether a planet remains rocky or pure gassy? And once we identify those key parameters, can we use them to understand some of the interesting patterns that have emerged when we zoom in to individual classes of planets? For example, I briefly talked about the physical distinction between the super Earths and mini Neptunes. That's most easily seen in the radius versus orbital period. Zooming into this particular region, we see a very clear radius gap that separates the two populations. So what is the origin of this radius gap? And for these large planets, even though the hot Jupiter is rare, as they go to longer and longer orbital distances, their population starts to rise up. And in fact, we see a peak between 1 to 10 AU. That seems to suggest that there's some preferred formation location of these gas giants. So why is that the case? What is so special about that particular location? Let us first begin by identifying these key parameters that control what kind of planets that we're going to end up with. So there, the question is really about the planetary mass growth, and in particular, the gas mass growth. Planets form in a protoplanetary disk. So here's a slice of a protoplanetary disk. We're going to start at a point where the planetary rocket core has already assembled by the coagulation of the solids in that disk. Let's also say that this core is massive enough so that we can define its gravitational sphere of influence, which is the minimum between the Bondi and the Hill radius. So within the sphere, the gas can be gravitationally bound to the core, but that binding process, the release of the gravitational potential energy, will create a non-zero temperature gradient. And for any system that has a non-zero temperature gradient, that system always likes to erase away that gradient by cooling off. And when you have a layer of the gas that is trying to cool off, it's going to shrink. which leaves some room for the ambient gas to refill this gravitational sphere of influence so that this planet can grow its gaseous envelope. So from that simple thermodynamic consideration, we can write down completely analytically how the planetary gas mass grows as a function of time, and also with respect to some of the key physical parameters. So let's start writing it down by realizing that in this picture, the growth timescale is really just given by the cooling timescale of the envelope, which to order of magnitude is just the energy content within the envelope divided by the cooling luminosity or the cooling power. Throughout this entire cooling process, the envelope remains in hydrostatic equilibrium, which means we can write down the energy content as a gas mass sitting in the gravitational potential of the core. Now, as for the luminosity, to figure out the luminosity, we need a better understanding of the thermal structure of these planets. And in general, we have the outer radiative zone and the inner convective zone. The reason why this occurs is because as you go to a deeper and deeper and hotter layer, you hit a point where the temperature is hot enough so that you have a dissociation of hydrogen molecules, which will allow the creation of the H- ions that become a strong, dominant source of the opacity. In fact, the H- opacity is a very strong function of the temperature, so that as you go to even deeper and deeper layer, you're going to see a surge of the opacity, which means it's extremely difficult for the energy to be transported out by radiative diffusion. So rather, it's the convection that prevails. Furthermore, most of the mass is centrally concentrated so that about 90% of all the gas is locked into this inner convective zone. That means the bulk cooling timescale of this envelope is given by the cooling timescale of this inner convective zone. You might recall that when it comes to convective energy transport, what controls the rate of that is the thermodynamic properties right at the lid of that convective layer. And there are different ways to explain this and understand this, but I think one of the best way to understand the physical phenomena is to see what happens in everyday life. So here is a little demo that I made a while ago, but it's so simple to make that I reenact this every time I teach a fluids class. Pardon me, that's not supposed to show. Here we go. So this is hot tea, and I'm pouring cream so that I can use the cream layer as a tracer of convection. And what I'm going to do is I'm going to change the temperature right at the boundary of this medium and see what happens to that convective motion. So right now, I'm just waiting for the sloshing to die down. That rising motion, that is not convection. That's just sloshing or surface gravity wave that I've generated by the pouring motion of the cream. So we're just going to wait until that dies down. And once that's more or less settled, I'm putting metallic lid on top of this glass so that I can easily change the temperature at the lid by placing ice cubes on top. So that was one ice cube. And that's the second ice cube. Notice what happens to the cream layer. It starts to rise. In fact, it creates some global dredge up so that you have a complete tea cream mixture within a few seconds. You might have noticed that I placed a third ice cube, and that really invigorates, speeds up this entire process. Okay, and if you wait just a few more seconds, you really have a complete tea cream mixture, all by putting ice cubes on top. I have not done anything else to the system, just putting ice cubes on top. Okay. So this is a demonstration of how, when it comes to convection, it's really what happens at the very boundary layer that controls the rate at which the convective energy transport occurs. And of course, this is expected because what I've done here is I have created a steep temperature gradient, which is a criteria for the triggering of convective instability. So going back to the exoplanet, that means the rate at which the energy gets transported out of this convective zone and into the radiative layer is all given by the thermodynamic properties right at this radiative convective boundary. So we can write down the cooling luminosity at the radiative convective boundary, which by definition, it can also be written as due to the radiative diffusion. So this cooling luminosity then is going to scale with the photon mean free path, which goes inversely with the density and therefore inversely with the gas mass. Combining everything together, the gas mass will grow as a square root with function of time. But of course, there's also the opacity. And with a more careful calculation, we can derive the full scaling relationship and identify 3 key parameters that control how thick of a gas layer a planet is going to have. So those 3 key parameters are the time allowed for the gas accretion. This is the time between the point at which the rocky core has assembled to the complete dispersal of the disk gas. It also depends on the metallicity, so the elemental abundance within the envelope. The less metals the gas has, the less opaque it is, so more transparent, it's going to cool faster, and therefore it's going to grow faster. That's why there's an inverse relationship. But by far, it is the mass of the core that is the most constraining, it's the most sensitive. And this just makes sense because the more massive the core is, the easier it is for that massive core to gobble up and hold on to a thicker and more massive envelope. So for the first part of our discussion, I'm going to focus on the properties of the core, when the core assembles and how massive it is. And later on, when we talk about the gas giants, we're going to come back to this effect of the metallicity. Now, there are 2 points at which that simple scaling relationship starts to break down. The first is at the high mass end, where it's easy for that massive core to build such a thick envelope that the mass of the envelope itself becomes comparable to the core mass. That's mz, the core mass, mxy is the envelope. And at that point, you have to worry about the self-gravity of the envelopes. Recall that throughout this cooling process, the envelope has to remain in hydrostatic equilibrium. That means you need very large power to keep that massive gas from collapsing under its own self-gravity. But if you have large power, you're going to accelerate that cooling process and therefore the gas accretion process. So you just made the problem worse by having even thicker and even more massive envelope. So you're just going to keep on making the problem worse and worse until you cause a catastrophic shortening of the cooling time and therefore a super exponential growth of the total planetary mass. And this is the classic runaway gas accretion. This is a classic solution to how we can create the gas giants, including our own Jupiter, with the caveat that, of course, this cannot go on to infinity. Eventually, it's going to be halted by the hydrodynamic effects rather than the thermodynamic effects, where the hydrodynamic effect could be local or global, where the global hydrodynamic effect is just from the overall global accretion of the gas throughout the disk onto the central star. At the low mass end, you have what is called the maximum envelope mass given by when the entire envelope just thermally relaxes to the outer nebula. Recall that this cooling process occurs because the system is trying to erase away a non-zero temperature gradient. But for a very light core, the path to the complete thermal relaxation it can be short. So when you completely erase away that temperature gradient and have a completely isothermal envelope, you have nowhere else to go. You have completed the cooling process. So you're done. This is going to give you the maximum possible envelope mass. Combining all of this together, we can draw the expected envelope mass fraction as a function of core mass, color-coded with respect to when the cores assemble. The yellow points are the cores that have assembled so early that they had the full disk lifetime to build their gaseous envelope, whereas the purple points are the ones that have assembled so late that they barely had any time to build their gaseous envelopes. Now, as a function of core mass, you will note that there is some pretty clear upper envelope. These come from those different limitations on the gas accretion. So at the lowest mass end, this comes from that maximal isothermal limit. At intermediate masses, we have that still cooling curve given by the scaling relationship that we have derived. At the high mass end, we have the triggering of the runaway and the halting, the global halting due to the disk accretion. So as a theorist, I can give you the expected envelope mass fraction as a function of core mass and also as a function of time. But observers only have access to present day size of the planets and sometimes the mass of the planets. Luckily, there's almost one-to-one relationship between the envelope mass fraction and the size of the planets. So these points are over here with a very thick envelope, those are, of course, the gas giants. The intermediate range, those correspond to the mini Neptunes. And once the envelope mass fraction falls below about 10 to negative 4-ish, that's where you have the practically rocky planets, the super Earths. Now, let's take a look at what kind of region these planets occupy in this phase space and think about the formation conditions. These gas giants, for example, occupy a very tiny fraction of this entire phase space. And that's because not only do their cores have to form very early, they also have to be massive. They have to be more massive than about 10 Earth masses. By comparison, these small planets, they don't have any restriction on core mass. They just have to assemble relatively late. And this stringent formation condition for this gas giant may be the reason why they are so much rarer as compared to their smaller counterparts. Furthermore, this stringent formation condition can also manifest in the variation of planet population as a function of things like the host star metallicity or the elemental abundances of the host star. The logic is that if you want to create the massive cores, that's more likely to occur in a more metal-enriched disks. And at least on a global sense, we would expect the metal-rich stars to be encircled by the metal-rich disks. So then, because the gas giants can only appear from the most massive cores, we would expect the giant population to be strongly dependent on stellar metallicity. And in fact, this is exactly what we found observationally all the way back in the mid-2000s. But for the small planets, because they don't have much of a constraint on what kind of cores they need, we would expect a much weaker dependence of the small planet population on host star metallicity. And with more modern observations, indeed, this is what we find, where the small planets have much weaker dependence on the host star metallicity as compared to their large planets. So the simple consideration of the thermodynamics, hydrodynamics, and the gas accretion physics can already give us the prediction already gives us a good agreement with what we currently find in terms of the connection between the planet population and the properties of the host star. Okay, so with that understanding of the underlying gas accretion physics, let's now use that idea to look at some of the interesting patterns that have emerged in individual classes of planets. Let's first start with the small planets, where we see this clear radius gap that separates the smaller rocky planets from the more gas-enveloped mini-Neptunes. Now, I should preface by saying that the existence of this radius gap was predicted by theorists, not from the gas accretion physics, but from the mass loss physics. So there are two flavors of mass loss now, but the original mass loss theory is by what is called the photoevaporation. So here you have a planet. This is a rocky core with a gas envelope on top. And these operate when the planets are close to the star. So let's say this planet is a short orbital periods. It's been bombarded by a high flux, high stellar photon flux. And in particular, in the X-ray and UV, those will ionize the upper layer, which thermalizes with the surrounding gas and drive off a wind. And even if you have started with every single planet being gas envelope mini-Neptunes, this will create a gap between the two populations by simply transforming those that were at particularly short orbital periods, get rid of all their envelope, and transform them into the bare rocky objects with a clear demarcation and separation between the two populations. Now we have a second flavor of mass loss, and that's called core-powered envelope mass loss. Here, the idea is that the core also contains some thermal inertia, and it's going to cool over time, which means it's going to transfer its heat to the surrounding gas. And that will puff up the planet, which will puff it up beyond its boundary radius, and that's also going to drive off the wind, and you can calculate the rate of mass loss using the classic Parker wind solution. And that can also create the radius gap with a clear demarcation between the two. Now, just like the photoevaporation, this is also dependent on the stellar flux. In particular, in this case, is the bolometric flux, because the exact rate at which the mass loss occurs is set by the temperature at the boundary radius. So it's the equilibrium temperature that matters here. The upshot is that for the mass loss calculation, we would expect much fewer rocky planets the further and further away from the star, just because these mass loss processes lose their potency at longer and longer orbital periods where the stellar flux just diminishes. And in fact, that's exactly what we see. We don't see any rocky planets beyond around 20 to 30 days. But you take a look at the exoplanetary data, and if anything, we might even have an abundance of those small planets at these long orbital periods. And furthermore, our solar system is basically rocky planets at longer orbital periods. So given this, how can we reconcile the fact that there may exist quite a large population of these long period rocky planets and the existence of the radius gap? And what I'm going to show you is that using that gas accretion physics that we have just discussed, that can already very naturally create this radius gap before there's any mass loss. So to see this more clearly, let us go back to the expected gas mass versus core mass. Here, I'm actually showing a different orbital periods, and I'm limiting to a particular time frame. And just like before, at the low mass end, we see the huge drop-off due to that isothermal maximal limit, a much shallower curve due to that cooling process, that power loss scalar relationship that we have defined. At high mass end, we see the triggering of the runaway and the halting and the global limitation due to the disk hydrodynamics. Now, when you have such a steep drop-off and a comparatively much shallower slope in the gas mass versus core mass, this is going to directly translate into a relative deficit and relative excess of the planet population in terms of their sizes, even if you have a completely featureless flat distribution in the core masses, like what we see here. So here, the filled histogram is drawing from a completely flat, featureless underlying core mass distribution. The filled histogram makes a correction for the fact that in nature, we don't see that many massive cores. In fact, we do see quite a steep drop-off once you go above around 8 to 10 Earth masses. So this just accounts for that. So indeed, we do see some relative deficits and excess. So why do we see that? So here, this huge population, these are pretty much just rocky planets. So these correspond to the gas mass falling below about 10 to negative 4, 10 to negative 5. You have so little gas that for these planets, their sizes are dominated by the cores. And the size of the cores, that's a very weak function of the mass of the planet. So it's going to show up as a relative peak or just a large population. What is interesting is that we have this a huge drop-off here. And that's because once the gas mass goes above about 10 to negative 4, so that this region, it's the gas mass that sets the size of the planets. But notice how you have such a small dynamic range to fill up this space. So that's why it's going to show up as a relative deficit. Until you hit the cooling curve where you have a much wider dynamic range to fill up that space. So it's going to show up as a relative excess. And the drop off here is just because we don't have that many massive cores. Now let's compare this to the data. Here's the data. Just like in our theory, we do see the rise of the population as you go to smaller and smaller rocky planets. We see a gap between about 1 to 2 Earth radii, gap between 1 to 2 Earth radii, peak between 2 to 3, peak between 2 to 3, and a fall off beyond 3, a fall off beyond 3 Earth radii. So purely from gas accretion physics, we can already explain the observed size distribution of the exoplanets. So just by characterizing the gap alone, we won't be able to tell whether this is a primordial population or those that have undergone mass loss processes. So what can we do to distinguish between the two and really try to test this theoretical idea? Because good theories must be testable. Well, one point is that if you do account for this primordial population, you will get quite a large number of this long period rocky planets as expected. And I mentioned how even in the current observational data, we see a hint of this long period rocky planets. Unfortunately, it's right at the detection limit for Kepler. So depending on which group you talk to, depending on what kind of statistical methods they have used to correct for the completeness, you can get very different results. But with the upcoming European mission Plato, whose entire major science goal is to figure out this population of the long period rocky planets, we should be able to answer this question. Are these truly rare, or are these actually more abundant than we thought? Which has an interesting implication about the uniqueness of our solar system, because again, we live in a system with a long period small planets. Now for a more direct comparison between the primordial population and the evaporated population, one of the best ways to distinguish that is to look at both the radius and the mass of these planets. So here, the circle points and the triangle points are the data. These are planets with the good mass measurements. It's a very small fraction because the mass measurements are really hard. And in contour lines, these are model predictions where the orange contour line is purely from formation and green contour lines are those that have undergone mass loss. From top to bottom, we're going from cores that have assembled early to cores that have assembled late. Just in general, the puffier planets require early core assembly. We have seen that already. For most of the mini Neptunes where we have the mass measurements, we do require this late time formation. However, what's interesting is that for the super Earths with the current mass measurements, which are biased towards high masses, they do require photoevaporation. It's really hard to explain this population purely from formation. So that's interesting. And again, to really test this idea of the primordial versus evaporated population, we do need a lot more mass measurements of these small planets. Notice how in a lot of the cases, we do see a much of a large tail, and most of the planets are expected to have smaller masses than what we currently measure. So if we can have a more follow-up to these small planets, more of a mass follow-up to these small planets, and see just how extended the mass distribution of these planets are, we would have a better idea of which one is the more dominant channel. Are these population being shaped purely from formation? And what exactly is the effect of the photoevaporation? So the mass measurements, while they're difficult, there's quite a bit of upcoming extreme precision radial velocity instruments being commissioned, so they would be a lot of help in trying to answer this question. All right, so those were for the small planets. Now let's talk about the large planets. And I'd always like to start this by making a comparison between the small planets and the large planets. And that comparison, that differences go beyond just their obvious, the obvious comparison being their size. Even if you look at something super simple like their orbital periods, they do show a different characteristics. For example, these small planets over here, the green, the turquoise, and the black, they look really flat in terms of their orbital period distribution. And that flat profile means that there's no particular preferred location for their formation, except there's a knee at around 10 days, and that could be explained easily by realizing that planets forming a disk, and disk has some inner edge due to the magnetospheric truncation from the central star. But for this discussion, I'd like to focus our attention on these large planets. Notice how for these large planets, their population just continues to go up. And this is from the transit survey. That's why it doesn't go beyond around 300 days. But from the radial velocity surveys, as we extend this population to wider orbits, we see a hint of a peak at around a few AU, which means that for these gas giants, they do have a preferred location. So why is that the case? What is so special about that few AU orbital distance? And here I'd like to go back to this 3 key parameters that control whether a planet becomes rocky or gassy. We've already talked about the properties of the cores, the time at which they form, and the mass of the core. But let us now focus our attention on the metallicity. And again, as a reminder, less metals, less opaque, more cooling, and therefore faster growth. So does this mean that few AU is where we expect some local minimum in the metallicity of this planet, of the underlying disk, so that the gas that these planets inherit are also less opaque, and therefore they facilitate a faster growth? We're going to answer that question by tracing metallic species with the grains. Remember, we're talking about a disk of gas and dust, and those dust interact with the gas. And from that dust-gas interaction, we actually expect to see a non-uniform radial and vertical gradient. The reason for that is the fact that the gas parcels and the grains travel at different speeds. So on the left, this is a gas parcel, that's a grain. For the gas parcel, if we consider the forces acting on the gas parcel, we have the stellar gravity pointing towards the central star. But because we're dealing with the gas, there's also pressure gradient force going in the opposite direction. That means this gas parcel is going to travel at a subcaplarian speed. So it's slower than the grains, which means that gas is going to drag on the grains and sap away the angular momentum, causing the radial drift of those grains. Now, the degree of that radial drift is a very strong function of the size of the grains. For example, if the grains are too large, then you have large inertia, so the drag is irrelevant. On the other end, if the grains are too small, then they very quickly equilibrate to the motion of the gas so that they just end up flowing with the gas. So again, radial drift becomes sort of irrelevant. That means there's an optimal size for the drift, and that is given by when the frictional stopping time, which is the time it takes for these grains to reach their terminal velocity, to be equivalent or to be on the order the local orbital time. For those of you who study the dust gas dynamics, this also means Stokes parameter being of order unity. Now, this explains the dust gas interaction, but the dust grains also interact with themselves by colliding with each other. And if the collision is energetic enough so that it exceeds the material strength of the grains, then you expect a fragmentation. But if the collision is not so energetic, then you might expect the growth by just a merger between the two grains. So combining the drift and the fragmentation and growth, let's try to construct the expected radial and vertical gradient of the dust to gas ratio, which we're going to use as a tracer of the metallicity. Let's start with the radial distribution. And we're going to start from the outer edge of the disk. At those outer edge, the dynamical timescales are so long that you're barely going to see any action. But once you go within, so down to about 10 AU, then the drift, then you now see the effect of the drift. And in fact, the drift is faster than the growth. At even closer in, now that the growth and fragmentation starts to catch up. And when it comes to growth and fragmentation, we generally expect that there is some special location within the disk. We call them the ice line. So this is the location beyond which the disk is cold enough that these grains are coated with the icy mantles. And if you are inside this ice line, the disk is hot enough so that those icy layers just sublimate away. And the classic expectation is that the material strength of those bare silicate grains are smaller than the icy grains. So on the inside, you expect to see a lot more fragmentation because they're just more brittle. So you already start with the smaller grains, but it just becomes even smaller. And recall how the smaller and smaller grains are less susceptible to drift because they're so well coupled to the gas. So in overall, you would expect a drain out of the grains from this region and a pileup of the grains in the innermost region, which means we would expect some kind of a local minimum between 1 and 10 AU. And with a more careful calculation, that is pretty much what we find for a range of possible exact value of this fragmentation velocity. So that's the radial distribution. Let's now take a look at the vertical distribution. And vertical distribution is important because the planet only has some limited finite reach. Remember how the gravitational sphere of influence of a planet is given by the minimum between the Hill and the Bondi radius. And in the background here, we're showing the level contours of the dust to gas ratio. The overall shape, the wavy shape here, that just reflects the radial gradient that we have just discussed. But here in the vertical direction, we see a lot more uniformity on the inside than on the outside. So why is that? When it comes to vertical gradient, there are 2 points, the two effects. There's a turbulent diffusion that likes to mix up all the grains and make it more uniform in the vertical direction. There's a gravitational settling due to the vertical component of the stellar gravity that tries to that tries to collect all the dust grains within the midplane. Now, in the inner regions, we have a lot denser gas. So the particles are more well coupled to the gas, and they're much more likely to be vertically mixed, coupled to that vertical turbulent motion of the gas. But on the outside, we have a much sparse gas, and the particles are less coupled, and they're more likely to settle down due to the stellar gravity. So that's why we see a lot more of a vertical gradient on the outside than on the inside. And overall, when we take a look at the reach of the planet, we do see that local minimum between 1 and 10 AU. The local minimum in the dust to gas ratio, and therefore the metallicity. So combining that with the gas accretion physics, indeed, we do find that the giant planets are more likely to form between 1 and 10 AU, which is exactly where we see a peak in the giant occurrence rate between 1 and 10 AU. So we have begun our discussion by starting from the final product of the planet formation, the exoplanets, and trying to go back in time using some first principle physics and astrophysics to figure out their origin channel. We first identified 3 key parameters that control what kind of planets we end up with: when the core assembles, how massive the core is, and the opacity of the accreted gas. And using that knowledge, we have zoomed in to individual classes of planets to understand some of the interesting patterns that have emerged in modern day observations. We first looked at this radius gap that separates the rocky super-Earths from the more gas-enveloped mini-Neptunes, and we've demonstrated how the primordial gas accretion alone can carve out this radius gap well before mass loss. And that mass loss, of course, it's probably going to further sculpt this population, but the effect may only be a second-order effect. So how can we test this observationally? We first need a better characterization of the long period small planet occurrence rate. We also need more mass measurements of these small planets. So upcoming Plato, which is a transit mission, will answer the first point, and more radial velocity follow-up will answer the second point here. And then we looked at the gas giants, trying to understand why is it that there seems to be some preferred location of their emergence between 1 and 10 AU. And we've demonstrated how the combination of the dust drift and growth naturally creates some local opacity minimum, and therefore a favored spot of Jupiter formation between 1 and 10 AU. So where do we go from here? So I'd like to close this discussion by talking about what I think are the next major milestones in the field of exoplanets and planet formation, as well as what my group is doing to address those milestones. First of all, among these 3 key parameters, by far, it was the mass of the core that was the most constraining. But right now, we don't really have a good understanding, a good theoretical prediction of what that core mass distribution should look like. So this is one of the major research avenues that my group is taking and will be taking over the next few years. And it's very timely because within that time frame, we'll see the launch of the NASA's Roman Space Telescope, whose one of the major goals of this telescope is to detect planets using the microlensing. And I'm super excited about this because this is a very unique detection methods. It's the only detection methods that will probe exactly this empty space that we have right now in the mass versus orbital period. So Roman is going to give us an unprecedented probe and detail into the bottom of the planetary mass function, which will be super exciting to be able to test against what we'll find from our theoretical investigation. Second, with the ongoing tests, the All Sky Transit mission and Gaia which have given us really exquisite precision measurements of the stellar properties combined with the ground-based spectrographs. There's a lot of interest right now in the field about understanding planet population and its variation as a function of stellar parameters. So we talked a bit about stellar metallicity, but there are many different axes one can take. So stellar age, metallicity, the spectral type, and the galactic environment. So this is one of the major avenues that my group is actively working on right now. How does the planet formation efficiency change as the properties of the host stars change? And finally, at the very beginning of this discussion, I've highlighted the need to bridge the gap between what we observe as the initial condition of the planet formation from disks and the final product of the planet formation from the planets. For this lecture, I've talked about how one can go from the final product and work backwards in time. We can also do the other way by looking at the disks and go forward in time. So that's another avenue that my group is taking by a combination of the analytic investigation as well as numerical hydrodynamic simulations, trying to understand some of the interesting observations that are being measured using the ALMA for the protoplanetary disks. And try to figure out what are some key observables that we can take from the disk observations to predict what kind of planets we expect to see as a function of the disk parameters. And furthermore, there's now a very much heightened interest in something super fine detail on the planets, like their atmospheric characterization. So can we make some prediction on the trends and the patterns that we would expect to see on the atmospheric properties of the planets as a function of things like the planet mass or their orbital period that will be tested with the JWST and upcoming European mission Ariel. So I'm very much excited about what we'll find with all this upcoming and ongoing space-based and ground-based missions, and that we can use to test the theoretical predictions that we're developing in my group. Thank you very much.
Thank you, Eve, for that wonderful journey through the formation of planets. The session is open for discussion. If anybody has questions, please use the reaction button to raise your hand. Yeah, Barnali, you can unmute. And
hi, thank you so much. It's just a really nice talk. So I was actually wondering how the theory takes into account of the different spectral type of the host star. So in particular, because you showed that the solar system planets occupy a very different region in the space phase than most of the exoplanets or the exoplanets that NASA have found. So I was wondering what fraction of those exoplanets are actually found around G-type stars. And yeah, that's my question.
Yeah, that's a great question. So actually, most of the planets are around FGK type stars. And that's because these missions were designed to, their goal was actually to find the solar system analog. It's just that by a pure surprise that most of them happen to be like very short period planets. That's one of the huge surprise in the exoplanet field. But yeah, most of those host stars are FGK. And I can also add that right now there's a lot of interest in trying to figure out what the planet population would look like around the M stars instead, because we live around the G-type star, but M stars are the most abundant kind of stars in our galaxy. So if our goal is to figure out what's the most common type of planets in our galaxy, it makes sense to look at the M dwarfs.
Thank you so much.
yeah, Alak, please go ahead.
Yes, you have mentioned in your last slide the galactic environment plays a role in the efficiency of planet formation. Now, suppose instead of looking at disk stars, you are looking at stars in crowded environments, either in globular clusters or in open clusters, where not only the environment is very different, but their metallicities are also quite different, and there is also a spread in the metallicity. So how do you think that planets around stars in globular clusters or open clusters would have any kind of a distribution differences with respect to what you might be finding in the disk of the galaxy?
Yeah, that's a really great question. One way that my group has looked at is the different radiation environment for the different clustering. So for this, we've actually looked at a more massive clusters. So the idea there is that when we take a look at the stellar clusters, when we take a look at the young clusters, the stars are correlated spatially. So that actually has a really interesting implication on what kind of a background radiation environment these planet-forming disks have. And it's quite severe in that to a first degree, you would expect a very different chemical composition of those planet-forming environment. So that we would expect a different kind of like elemental abundances in the planets that may form. And if you take a look at something that was sort of like the progenitors of the globular clusters, which would be even more massive, then this becomes even worse in that the radiation is so severe that you can really destroy the planet-forming disks over a very short time scale, which means it's really hard to form the planets. And what's interesting is that there are some observational hints that around, let's say, the thick disk stars, that the planet occurrence rate is actually reduced. So that is one thing that my group is currently working on, and we do find that we would expect a reduced planet population around these more clustered environments.
What about dynamical effects?
Yeah, great question. So for dynamical effects, turns out that the stars, the stellar dynamical effects don't quite do much to the planet hosting star, just because it's quite farther out. The planets, especially the inner planets, they're more likely affected by themselves because of the proximity. And if not, if you have a gas giant just outside, but not so much the stellar flyby, unless the stellar flyby can really, really disturb inwards of like 1 AU. But that's a very chance encounter. In most cases, you don't have that. So it's more of a radiation. We find that it's more of a radiation that has a huge impact, and rather than the dynamical impact of those surrounding stars.
Thank you.
Thank you.
Neil, please go ahead.
Thanks for the wonderful talk, Professor. My question was, where do moons fit into all of this, and what has the exoplanet community done for detection and characterization of exomoons?
Yeah, so the exomoons are slowly, we're slowly getting interested as an exoplanet community to see like whether exomoons are detectable. I think it's getting a very slow traction because the initial purported detection turned out to be sort of spurious. Like it just turned out to be, I think it was from HST, and it just turned out to be the instrument effects from the HST. So I think there are definitely interests. It's just that like with the caution, because it's such a tiny effect, and like we want to be careful about whether it's really detectable or not. But there's an increased interest in things like exo rings and exomoons, and it's I would say like it's slowly getting traction.
Thank you.
Okay, are there any? Yeah, Indulekha, please go ahead.
Yeah, I don't know whether I missed this. What about binarity or multiplicity of the stars?
Great question. Yeah. So around binaries, we have a very limited sample of the planet detection around binaries. So and it's mostly around circumprimary planets within a binary system. So there, what we find is that there's some edge to the planetary system. And that's we think that's there's some debate about whether that's carved out by like post-disk dynamics, but I think the general idea is that already within a binary system, it sculpts a different kind of a disk and a different kind of like migration history for the planets. So in general, it just creates some kind of like a cutoff and where the planets could fit within a binary system.
Thank you.
Okay, looks like there are no further questions from the Zoom participants. Oh, I do see further hands raised. Barnali, you had another question?
No.
Yes. Oh, sorry. Sorry. Can I ask another question?
Yeah.
Yeah, I was actually curious about one thing. So we don't hear much about planets possible around early type stars. So I was wondering whether theoretically that is allowed for these hot stars to have planets, and if yes, what kind of properties and how will they differ from the population that we actually observed?
Sorry, I think I missed that. What kind of star were you asking?
Early types OBA stars, so we don't hear any discussion about those. So I was wondering whether theoretically it's allowed for them to have planets around them, or is it something that they can't have because of their orbits? Yeah.
Yeah, great question. So around A stars, there have been efforts, especially using tests. Despite the efforts, we haven't found many planets. So like just generally these massive stars they have short lifetime, so there's a limited window in which we can actually detect the planets. And we also think that the lifetime of the disks around the more massive stars are very short compared to like the FGKs and M-type stars that we're studying. So that means there's a very limited window in which the planets can form. So like that could be the reason why we just like even physically we just don't expect to see many planets around them. So like that's one of the reasons why there's just not that much discussion around of the planets around this like more massive stars.
Okay, thank you.
Alak, you had another question?
Yes, if I may ask another question.
Please go ahead.
You referred to the radiation environment in your answer to the question about dense stellar environment. Now, one of the very early systems where exoplanets were discovered were these planets around neutron star pulsars. Pulsars which are giving out large amount of radiation. And this is not the kind of radiation that you see in an ordinary stars. These are highly energetic radiation. Yet these planets not only have formed, but they have also survived. So does this example sort of run some kind of counterpoint to what you just said?
Yeah, that's a great point. And I'll say not necessarily, because it's likely that those planets, like if they have formed from the very beginning, it's actually really hard for them to survive, and there are calculations that show that they will not survive. So more likely what happened was that either the planet has formed initially farther out, and then it got dynamically scattered in, or it could also be that there was sort of like a second generation of the planets. I think people call this like a zombie planet, like a second generation of the planets that have formed around the circumstellar material around a very much evolved star. Not much calculations have been done on that front, but I can definitely tell you that those were not the first generation planets, because they would not have survived.
Thank you.
Chanda?
Yes.
There's some issue with your audio, Chanda. We don't hear you.
That you need very different.
Chanda, I think there's an issue with your audio. We couldn't hear your question. Could you please type it out in the chat?
Jupiter type planets to form. Yet
I'm sorry, Chanda, we couldn't get your question. If you could please type it out. Can you please type it out? I think there's some issues with your audio.
Planets. So I was wondering if other stars also have
I think we really have some issues.
Can
Right?
you
No, Chanda, we couldn't get your question. So can you please type it out in the chat box? In the meantime, we'll ask Abhishek to go ahead with his questions.
Yes, thanks. Nice talk. Thank you so much. I just have a very generic question. So you have calculated the cooling time scale for, let's say, some of the planets. And then if you, let's say, multiply it with the sound crossing time, you will get a cooling length scale, right? So does that length scale sort of, have any correlation with the radius of the planet, or anyhow, is there any such analysis been done?
So cooling time scale would be just energy divided by luminosity. I think you were talking about the dynamical time.
Right.
So yeah, so that would be actually that would actually be more relevant for the time it takes to reestablish the hydrostatic equilibrium. So that one you would take about the radius of, well, yeah, I mean, for like, you have to do this for each of the layer, but like, let's say like on the order, the radius of the planet versus the sound speed. So that time scale is really short. And that's the reason why we can say that throughout this cooling time scale, the cooling process, the planet maintains its hydrostatic equilibrium. So just to give you some idea, that the dynamical time is on the order of days, the cooling time scale is on the order of million years.
All right. Okay. Thanks.
Okay. Chanda, would you want to give it a try? Again, asking a question. Yeah, she has typed it out. Yeah, let me just read out. Chanda, I'll read out the question. Yeah, the question is, you showed that Earth-type planets and Jupiter-type planets require different conditions, yet our solar system shows different types of planets. Do you think this is common around stars?
Yeah, so that's a good question. So remember that there was a peak of the gas giants. Our solar system giants lie within that peak. So it's actually quite it fits for giants. It fits within the picture of the exoplanets, the exoplanet statistics. So again, like this could be explained by just that, like there's some favored location within the disk for the giant planets for a given core, and if you and that's because at that, like between 1 to 10 AU. So just to give you some idea, our solar system giants, the Jupiter and Saturn, they are within the peak and sort of like near the outer end of that peak. So they lie within the region where we expect to have some local minimum in the metallicity, which is what you require to have this gas giant formation. But if you're inside that, let's say like within 1 AU, then those regions are not very suitable or not very natural for the gas giant formation. So for those regions, you would expect to see like a smaller planets. So in the general sense, our solar system does fit the picture. And I think there was a second question in the chat. Have you seen different planets around a single star apart from our sun? Most of the exoplanet statistics are from a single star. There's only a very few planets around binary stars, and that's just part of a sort of human design. Just for simplicity, people have sort of like gotten rid of the binaries in their sample, but yeah, most of the planets that people quote as the detected and confirmed planets, those are mostly around the single star.
I suppose her question was connected with the first one, in the sense of, do you see, Earth-like as well as the high mass Jupiter-like planets around another star, for example, than our sun?
Yeah, good. Right. So actually, we do in the exoplanetary data, we see a correlation between the systems with the outer giants and the inner planets. So, if the system has the outer giants, they are likely to also have the inner planets. So in that sense, yes, that sort of general picture does fit with the solar system. It's just that those inner planets for the exoplanetary data are something that we don't see in the exoplanets. So again, like these are shorter period planets with the size between that of the Earth and Neptune.
Okay, I don't see any other hands raised. Sarita, any questions in the YouTube?
Yes, there's one question. The question is from Arvind Parajpe. He wants to know whether Dr. Ebli can say something about the Goldilocks zone. What type or mass of stars would have this zone? This is more of a popular science question. That's what he said.
Yeah, so the Goldilocks zone usually refers to what the scientists call the habitable zone. So that basically refers to the region within the system where we expect to have some liquid water. So this goes back to the idea of can exoplanetary systems harbor life? So yeah, I mean, the Goldilocks zone or the habitable zone will just like shift depending on the type of the stars, because it depends on the flux of the star. So going back to like one of the very early questions about the spectral types of the stars. Another reason why a lot of the exoplanet scientists are excited about the M dwarfs is because that the habitable zone shifts inward. So that means it's much easier to detect planets within habitable zone around M dwarfs. And as you go to sort of like FGK, it's going to shift outward so that it becomes like harder. And of course, it's going to be even harder as you go to like the more massive stars. So that zone just like shifts around depending on, it shifts in around the less massive stars and shifts outward around the higher mass stars.
Okay, I don't see any further questions, no more hands raised. So let me thank Eve for this wonderful lecture and also for very patiently responding to all the questions. I'll now hand over the session to Dipankar and Sarita. Dipankar, over to you.
Yeah, thanks, Anupama. I think Sarita